All right, so you've just seen the solution for exam 1. There is a homework assignment due on Wednesday, and I emailed that to you on Friday before the... Garrett, do you have a question?
Yeah, sorry. Do we need to hole punch these in our notebooks? I forgot.
Yeah, I'd suggest that you keep these in your notebooks. Yeah. Any other questions before we continue? All right. So the next homework assignment's due on Wednesday, and then the demand estimation portion of the project is due on Monday of next week. So I got a couple of good questions about the project over the weekend. If you're not able to find like flow demand data for your specific city, then consider getting flow demand data for an adjacent city. So for example, if your city is Cleveland, Ohio, and you've just Googled flow demand per capita, water, drinking water, Cleveland, Ohio, like some important keywords, and you're not finding anything, try Akron, which is just down the road. Or if you can't find anything for an adjacent city, then you could try finding statewide average data, because there might be something specific to the state of Ohio that's more meaningful than a national average. So the basic idea is I gave you some pretty old nationwide flow per capita demand data, and if you can find something more recent and more locally applicable, then that'll certainly give you better demand estimation. So I don't think you should spend days and days searching online for flow demand data, but I think if you spend an hour, you can probably find something better than what's posted as that PDF file on Blackboard. All right. The other thing I wanted to revisit from the recorded lecture, I was thinking, if we had a quiz today, how many of you would be able to define flow regime? Flow regime. All right. So definitely watch that recorded lecture from Friday. Flow regime is something that you need to know to solve the homework that's due on Wednesday. So it was one of the last slides. Here it is, flow regime. So Froude number, flow regime, really important stuff. We're going to come back to Froude number a lot this semester. Let's just get some more practice, though, with trapezoidal channel geometry. We've touched on this earlier in the semester once, but let's revisit, because trapezoidal geometry complicates a lot of our calculations, and we have to be pretty good at calculating things like the area, wetted perimeter, hydraulic radius, and so on. Okay, so you can see that we've got a trapezoidal channel here that's 15 meters wide at the bottom and 35 meters wide at the top. And then here it's saying t equals 2. So what that means is the side slope is 2 units of horizontal for 1 unit of vertical. Okay, so let me draw this on the board, this trapezoidal channel. Okay, so it's at the bottom 15 meters and 35 meters at the top. Now it doesn't explicitly tell you how deep the water is here, but we can figure that out because the side slope is defined. Since the side slope is 2 to 1, what that means is that for every unit of for every unit of depth, there are 2 units of width on the side. So what we know is that this top part, which is 35 in total, has 35 in total. This part of it is 15. And so it's also prismatic, which means this segment on the left and the segment on the right are both the same length. And so you're like, this has some length L, and this has some length L. What is L? 10 meters? Good. So it's 10 meters on either side. So basically, it's already getting a little bit sloppy. Let me redo this. It's basically 10, 15, and 10 for the top width. So 10, 15, and 10. So that gives us the 35 that we see on the drawing. Okay, so if it's 10 over here on this side triangle, 10, and what we're told is that for every unit of T, 2, there's 1 unit of vertical, right? So T to 1 should give us a hint of what the depth is. So this depth y, if we have 2 units of width across the top for every unit of depth, then I think that tells us that y is 5. So any questions about that so far? All right. So with that known, let's just see all of the variables that are defined here. We've got lowercase b is 15 meters. Capital B, which is the top width, is 35 meters. T equals 2, y equals 5. So use these to calculate the area, wetted perimeter, hydraulic radius, and hydraulic depth using these formulas across the top. And that comes from chapter 10 in your book, table 10.1. It has it not only for trapezoids, but it's also got it for, you know, triangular channels, for half circles, ellipses, a variety of different shapes. But for now, we're just dealing with trapezoidal channels. So you'll notice for wetted perimeter, there's this intermediate parameter W that you'll need to calculate. But I think everything that you need is given there for area, wetted perimeter, hydraulic radius, and hydraulic depth. So the area should be 125 square meters. The wetted perimeter, 37.36 meters. Hydraulic radius, therefore, 3.34 meters. And hydraulic depth, 3.57 meters. Now, hydraulic depth is a strange one. What hydraulic depth is basically telling you is if this channel was rectangular rather than trapezoidal, how deep would the water need to be if it had a width of the top width? So it's basically saying take the cross-sectional area of the channel that you've got, so in our case 125 meters, and if the channel was 35 meters wide, how deep would the water be to have that same overall cross-sectional area? So not particularly important quite yet, but we will use hydraulic depth a bit later. Okay, so any questions about this trapezoidal geometry and calculating the parameters? So I think the key is to become familiar with this side slope factor. Maybe once you've got the lowercase b and w and p, you know, like it's pretty easy to plug the variables in the equation, but the sometimes the tricky part is just interpreting, you know, what is going to be the depth of flow given the top width and the bottom width, or maybe you are given the depth and then therefore you have to calculate the top width, capital B. All right. This is a side view of water. Here's the water surface. So you see the triangle and the little ripples? That means it's open to the atmosphere. And this cross-hatched section at the bottom just represents the base of the channel. And you can see that the channel is inclined. You know, water is flowing downhill in this instance. And the water depth is decreasing, which probably means that there's maybe some sort of a cliff at the end. You know, there's like a drop-off. Now, what we're looking at here is a force balance. So think about if we go down through water, the pressure increases, of course, according to the hydrostatic equation. So this increasing hydrostatic pressure distribution, if the pressure is integrated over some area, that means that there's a force pushing on this control volume of water from the left towards the right in the direction of flow. Now, if we wanted to do a force balance, we could also look at the forces that are resisting that movement. Here at location 2, the control surface that we've drawn, there's a pressure that increases as you go down through the fluid, but it's going to be pressing in the opposite direction. So there's the force that's pushing it forward, backward. The weight of the water is acting downward. So here, A times delta X is just the volume of water. So A would be taking into account the distance into the page as well as the depth. And then delta X you can see is the distance between 1 and 2. So A times delta X is the volume, and then gamma gives us the weight of the water. And then down at the bottom here, anybody know what this force is related to?
Friction.
Good, that's right. It's friction. So shear stress times an area is the force of the surface resisting the movement of the water. So the bottom of the channel is pushing against the water in the opposite direction of flow. So here delta X you can see is the distance between 1 and 2, and P would be the wetted perimeter of the channel. So if it's a very, very wide channel, it's only the width of the channel that is important in the wetted perimeter. The edges don't matter so much. But it's basically, it gives us an area times the shear stress, and therefore we've got units of force, the same as everything else. So this force balance, right now there is not an equilibrium in the forces. And the way that we can tell that there's not an equilibrium is by considering the velocity at location 1 versus location 2. Now, the flow rate at 1 and 2 is the same. So Q at 1 and Q at 2 is the same. So conditions here are steady. They're not changing with respect to time, but they're not uniform. So remember the difference between steady flow and uniform flow. Steady means that flow conditions aren't changing over time. Uniform flow is when the flow conditions aren't changing in the direction of flow. Here, it's non-uniform because at location 1, the water is deeper than at location 2. So that means it's non-uniform flow. The velocity is changing between 1 and 2. Even though the velocity isn't changing with respect to time, velocity is changing with respect to position. So in other words, we have convective acceleration that's occurring here. So conditions are not steady because of an imbalance in forces. There is less of a resistance at 2 than the force at 1, which is causing the water to accelerate in the direction of flow. So the velocity at 2 is bigger than the velocity at 1. And that acceleration between 1 and 2 is because of the imbalance in forces. So we'll spend maybe our last 2 weeks dealing with non-uniform flow, and it's pretty complicated. And there are some computerized tools that have been developed to help with the calculations of how do you find out what the new depth is if you've got non-uniform flow. But for now, we're going to look at if conditions are uniform, and that's pretty easy. If flow conditions are uniform, then trying to calculate the depth is pretty straightforward. So this is uniform flow. See how the water depth isn't changing between the upstream and the downstream location? The two depths are the same. And some of the indicators for that is that the water, the bottom of the channel is parallel to the water surface, and that is parallel to what our book calls the total energy line. Your fluid mechanics book called that the energy grade line. It's the depth of the water plus the velocity head. So all of these things are parallel. That's one of the indicators of normal depth. Now, by the way, so I asked you about the Froude number and flow regime earlier. That came from Friday's lecture. Another really important thing that you need to pick up from Friday's lecture is in the energy equation for closed channel flow, there are three places that the energy can be. The energy can be in the pressure head, the velocity head, and the elevation head. So these three things together we said was the total head. This is if the water's in a pipe. Like pipe flow was exam 1. Exam 2 is going to be open channel flow. So this was part of the energy equation when we were doing pipe flow. The three places that the energy can be when you've got open channel flow is the elevation, the velocity head, but not anything to do with pressure, because this is open to the atmosphere. So the water isn't pressurized any more than, of course, the hydrostatic equation, but Z will take into account the elevation above some datum. So it's actually the depth of the water that is taking the place of the pressure head term when we're calculating the specific energy in open channels. So this is another key point that you definitely, your ears should perk up when you're watching that lecture from Friday, because it's really important, and we're going to use this equation on dozens of occasions through the remainder of the semester. So I just wanted to reiterate and highlight that we're no longer going to talk about pressure head terms when we discuss energy and open channel flow. All right, so just back to this diagram again. We've got the water surface, the energy grade line. Here is the channel bottom. All three of them are parallel. So Y naught is called the normal depth. And it's called the normal depth because it's what will occur when there are steady, uniform conditions. So it's not changing with respect to time, not changing with respect to position. Now, how do you get flow that's steady and uniform? It's almost always in an engineered channel. Like in an actual river, you're not likely to have the normal depth very often because rivers have meandering paths, they have irregular slopes, and the flow in and out is constantly changing in a river. So this normal depth, it's important to know, but it's rare that in nature you'd see water flowing at the normal depth. Most of the time you'll have unsteady flow. But we're going to talk about normal depth because all of our work that will help us to find the depth when conditions are unsteady or non-uniform relies on us understanding normal depth. Okay, so the shear stress that's being applied to the water as it's flowing downstream, the shear stress, we can calculate by multiplying the unit weight of the water, the hydraulic radius, and S sub F is the slope of the energy grade line. So if you look at the slope of the channel and the energy that's lost, when you've got normal depth, delta Z is equal to H sub F. So between 2 points, the energy that's lost due to the water going downhill is the same amount of energy that's lost due to friction. And it's not pipe friction. H sub F here is just friction as the water is flowing over the surface. And so there's equilibrium between delta Z and H sub F. What makes these lines parallel is the fact that delta Z and H sub F is equal. So when there's equilibrium, when water isn't accelerating, it's flowing at a constant velocity as the water is going downhill. That's because the energy loss is equal to the change in slope. So all three of these slopes are equal when the surfaces are parallel. The slope of the channel bottom, the slope of the water surface, and the slope of the energy grade line. Now we're going to use Manning's equation to estimate the flow velocity and the flow rate when we have normal conditions, meaning steady and uniform. Now Manning's is kind of an update of the Chezy equation, which we talked about earlier in the semester. And the Chezy equation suggested that we could predict the velocity by having some roughness factor c and then multiplying that by the square root of the hydraulic radius and the slope. But Manning did more observations and just showed that it was more often true that there was a better fit if the hydraulic radius was taken to the 2/3 power instead of taken to the 1/2 power. So Manning's equation has different friction factors. It uses an N value instead of a Ches-EC. And then also the hydraulic radius is taken to the 2/3 power. Now look that there's a difference between SI units and British gravitational units. So if you're using traditional units where length will be in feet, then you need to use this coefficient in front of it, 1.49. But if you're using the SI units where length is in meters, then velocity is just calculated with this formula with no prefix coefficient in front of it. So the N values, in other words, have been calibrated for SI units. Okay, so here is a range of different N values for different materials. And picking the right N value is sometimes an art as much as a science. But you can see that the more smooth a surface is, the lower the N value will be. So if you think about this friction factor being in the denominator, a small N value will give you a high velocity. But a big N value, like water flowing over an unmaintained channel, which has lots of roughness and resistance, a big N value would give you a relatively lower velocity for the same channel characteristics. So R to the 2/3 power tells you about the geometry of the channel, because it's taking into account the area and the wetted perimeter. And S, the slope of the channel, how steep it is also obviously going to influence the velocity. So if we wanted to calculate the flow capacity for a 1/3 meter rectangular smooth concrete channel, and the slope is 1%, then what we're going to do for that is, in this case, what I meant was 1 meter deep and 3 meters wide. So it means that Y is 1 meter, B is 3 meters. We want to find out what is the flow capacity. That means the flow rate, Q. So we're going to have to find the velocity and then multiply it by the area in order to do that. Okay, so smooth concrete. If we look at concrete, it has 0.011 at the smooth end, and then at the rough end, 0.020. And so rough concrete would be if it had been finished with maybe like a really coarse brush. I'm sure you've felt concrete before that's rough, and sometimes if it's been finished with a really smooth float, there can be a pretty big range in what it feels like. For this one, we're using N equals 0.010. 11. Okay, so that's on the smooth end. And if we just substitute that into Manning's equation, so the slope is 1%, and we need to have the slope expressed as a decimal for Manning's equation. So if it's 3 meters wide and 1 meter deep, then that gives us a cross-sectional area of 3 square meters and a wetted perimeter of 5. So therefore, the hydraulic radius will be the area divided by the wetted perimeter, and it's 0.6. Now, by the way, what if it had been 1 meter wide and 3 meters deep? Is it going to be the same thing? It won't, because the wetted perimeter is different. It's the same area. Like if it's 1 meter wide and 3 meters deep, area is still 3. But what is the wetted perimeter in this case? It's 3 plus 1 plus 3. So the wetted perimeter would be 7. So that would give us a different hydraulic radius than 3 meters wide and 1 meter deep. So it would actually give us a reduced flow capacity because there's more contact area to provide resistance. So it is important to get the depth and the width entered correctly so that you can account for the wetted perimeter. But in this case, what we do is multiply the area of 3 square meters by the velocity here. So I've substituted in the 0.011, a hydraulic radius to the 2/3 power, the 1% slope to the 1/2 power, and so that tells us that the flow rate would be 19.4 cubic meters per second in this situation. Okay, so any questions about this first use of Manning's equation? So Manning's equation only applies if flow is steady and uniform. It gives you what's called the normal depth, or if you're given the normal depth, you can calculate the flow rate, which is what we've done here. We were given the normal depth, calculated the flow capacity of the channel. All right, now, for a depth of 1 meter, what channel width will convey a flow of 30 cubic meters per second? So this is saying, in part B, it says we want to know how wide should it be. So B equals what for 1 meter of depth to find a flow rate of 30 cubic meters per second being able to be conveyed here. Now you might be tempted to think that you could just like linearly scale, you know, like what we found in this first part was 19.4 cubic meters per second for 3 meters wide. So you might think, well, I just need to make it a little bit wider, and you know, like the ratio of flow rates would tell me how wide to make it. But that's not true because of the issue of wetted perimeter. So to solve this next part, we just actually will substitute into Manning's equation. So Manning's equation is going to be Q equals area divided by the n value, hydraulic radius to the 2/3 power, slope to the 1/2 power. So if it's 30 cubic meters per second, and it's going to be B, the width, times 1 meter of depth, and our friction factor is 0.011, and now the hydraulic radius is going to be B times 1 for the area, and the wetted perimeter would be 2 plus B. That's going to go in the denominator because the wetted perimeter is 1 on one side, 1 on the other, and then the bottom width B. So remember, the hydraulic radius is area divided by the wetted perimeter. So this is the area, this is the wetted perimeter to the 2/3 power, and then our slope is 0.01 to the 1/2 power. So we need to solve for B to find what is going to be the flow rate. Now, you're going to have to be able to solve, like in your calculator, things like this. And so I'll provide you I'll email you a link that kind of revisits how to use the equation solver on the Casio calculators, if that's what you're using. I use the HP calculator. I see some people have TI. Whatever you're using, that's fine, but you need to be able to solve for an isolated variable in an equation like this. And in this case, if we do that, then we get that the width should be 4.264 meters in this case. And if you'd just done that idea of trying to scale the width by X%, you know, based on that we got 19.4 cubic meters per second with a width of 3, then that would suggest that the width would need to be 4.64. But it isn't a linear relationship between width and flow rate. So it only actually needs to be 4.264 meters wide to get the 30 cubic meters per second. All right. Here are some more n values. These ones come from chapter 11 in your book. And so it's showing, for example, if you have a channel that's lined with wood versus if it's lined with metal or earth, or floodplain areas where you may have like grass or crops that are not usually submerged, but when the water's flowing over them, there's quite a lot of resistance on things like dense brush. So if you've ever seen a flood, like recently, the Mud River was flooded down in Milton and through parts of Ona. When the water level gets really high, it's not moving much in the region that's close to the shore because there's trees and brush, and that's providing a lot of flow resistance. There is an empirical relationship between the diameter of grains in the bed and the N value. So like if you had gravel, for example, and you knew the median grain diameter of the gravel in feet, then you could use that to calculate the N value. And so just for instance, if you had gravel that had a diameter of 0.5 inches, and you wanted to find out what's the N value that applies there, then you could estimate the N value for that gravel that has a diameter of 0.5 inches just by converting it from inches to feet, putting it into this empirical equation, and it would suggest an N value of 0.02 as the N value. All right, it's 1:49. We're out of time. We're going to pick up on this example when we get together on Wednesday. Remember that between now and then, you've got homework 7 to work on. So I'll see you Wednesday.